Good day from Perth to all you in Australia, Sri Lanka, as well as to all who connect from all other parts of the world. I am Senaka Vailideniya, current editor of the IESL WA chapter. This is our 8th webinar, as Bandula, our current president, reminded me a few days before. On behalf of the committee and the members of the chapter, I am pleased to welcome you all for this very valuable, informative, and very technical webinars that we organize as part of our professional development program. I think COVID has physically distanced us, curtailed our traveling, but on the other hand, it also has gifted us with excellent technical developments to make us much closer and more efficient. Unlike before COVID, now we have more freedom and a greater audience through these webinars, which previously were not as widely used as today. So I would say this has come to us as a blessing in disguise. The key speaker presenter of today's webinar, organized by IESL WA chapter, will be Dr. Sanjeev Narendranath. I can see Sanjeev is there waiting for the presentation. I think Sanjeev has a very exciting presentation. Sanjeev is a chartered mining professional with over 20 years experience in the mining geomechanics. He has worked at biggest mining operations in WA, such as Super Pit under KCGM, as well as underground operations including Mount Charlotte. He also has worked as a consulting roles with COFE and Intratech Group, where he took responsibility for projects with Rio Tinto, BHP, Barrick Gold, Newmont, etc. for various commodities in Australia, Asia and Africa and across the world. And this introduction to Sanjeev goes on for a little while as well, because Sanjeev has a very illustrious career record that I think we must share before we start his presentation. And to give a few more words on this, Sanjeev also has been called upon to provide expert technical and forensic advice on several sensitive cases involving geotechnical engineering issues and disputes too. He has spent 1 year with mining regulator in Victoria as a geotechnical advisor, where he was responsible for providing advice to the Office of State Resource Minister on Victorian mine and quarry wall stability and safety requirement. That's an interesting role Sanjeev had before he joined GHD. In early 2018, he joined GHD as the technical director of mining geotechnical engineering. And since then, Sanjeev works for GHD. His one of key focus areas is brown coal mines in the Latrobe Valley region in Victoria. Spontaneous combustion of coal and its potential impacts on coal wall stability is an area where he has extensive experience, which he has used as the topic for today's speech. Therefore, today, Sanjeev will be presenting his presentation on related to coal. The topic today is spontaneous combustion in coal mines, challenges faced by all mine operators. So that's going to be a very interesting topic to discuss. So therefore, let's welcome Dr. Sanjeev for today's talk. And Dr. Sanjeev, floor is yours.
Thank you very much, Dr. Senaka, for that introduction. Really appreciate that. Now, I am sharing my screen. I hope everyone can see it. Please let me know if you can't. So the topic I'm going to be touching on today is around spontaneous combustion, which I think most of us are aware does affect coal mines, particularly black coal mines in the Bowen Basin and Hunter Valley. Whilst it is less of an issue in brown coal mines, it is nonetheless still a pertinent aspect that needs to be considered. And the topic of my case study is how we handle this at the Loy Yang mine, which is located in the Latrobe Valley region within Victoria. Now, just before I launch into our case study, and I know we've got quite a disparate spread of locations and experience base within our audience at the moment. Some of you are from Australia, different states, Western Australia, so on. Some of you are from overseas, Sri Lanka and other places. But just by way of Victoria, to this day, and that's 2022, 82% of the state's power supply is provided by brown coal. Now, there is a plan to transition it into renewables over the next 15 to 20 years. But at this point in time, the state is very much dependent on the reliability and the sort of accessibility of brown coal. Now, there used to be 3 operating coal mines, brown coal mines within Victoria, but since the much publicised, certainly within Australia, the much publicised closure of the Hazelwood mine, there's really only 2 operational mines now, which is the Yallourn mine, which provides about somewhere between 18 to 21% of the state's power supply, and the remaining, so circa 60%, comes from the Loy Yang mine. So the Loy Yang mine is very much a critical element within the state's infrastructure regime as well. And that sort of adds a bit of a nuance to what some of the challenges we encountered in this particular case study, which I'll touch on. So that's just a very high level introduction. Now, just an overview of what I'll be running through. I will be providing a very cursory overview of the geology of the Latrobe Valley. I'll also start talking around some of the mechanics, the failure mechanics that we need to be cognizant of from a geotechnical perspective, and how that has to be controlled, not only from an operational perspective, but also when we encounter unforeseen challenges, i.e. Spontaneous combustion. We'll then launch into our case study, which focuses around a critical area within the mine, specifically the southern slope domains within the mine, which actually hosted a lot of the critical infrastructure, the conveyors and so on. How we dealt with that particular situation, how we defended ultimately the analysis we undertook using a risk-based probabilistic approach, and how that ultimately led to remediating the area in question. I wanted to provide a very high-level overview of some of the geological conditions that we deal with. So here's a very high-level stratigraphic column of the Latrobe Valley, and this is sort of a conceptualized.
Sorry, we can't see your screen, Sanjeev.
You can't see my screen.
Yeah.
Okay. Can you see it now?
No, not yet.
Try sharing my screen again.
Yeah, I can see you, and I can't see anything on the screen.
Just let me know if that comes up.
Yeah, that's right. Now it is. Yeah,
Okay.
you can see.
Perfect.
Yeah, yeah.
Problem with 3 monitors sometimes.
Yeah, yeah.
Okay. Glad that's up there. So just confirming, everyone can see a long section that's through there. So what we have here is a long section through the Latrobe Valley. So these are all the coal seams that go through from all the 3 mines. The Hazelwood mine, which in this figure is referred to as the Morwell open cut, the Yallourn mine, and sort of on the very right-hand side, which is in a hatched red box, that's the Yallourn mine. Now, one of the things that is probably quite obvious at face value is the Yallourn mine, rather the Loy Yang mine on the right. Unlike the Morwell open cut or the Hazelwood mine or the Yallourn open cut, runs through multiple seams, and it's all below the groundwater table. So the fact that we've got multiple interseams that we have to contend with from a stability perspective, and I'll touch on very shortly how the interseams sort of control stability, as well as what the aquifer conditions also do from a underlying perspective, and how the pressures need to be controlled. So I will touch on the failure mechanics very shortly, but the Loy Yang mine does have a lot of complexity associated with it, and that ultimately governs the failure mechanics of our critical mechanism. Now, there are a number of potential instability mechanisms that come into play, but I'll touch on the primary one. The primary one is referred to as the coal block sliding mechanism. Now, what you can see over here is a schematic, essentially a schematic diagram just showing the forces that come into play that we need to control that ultimately govern stability. Now, the way stability is controlled within the mines, or rather what destabilizing forces that we have to contend with, I'll touch on the very first one. The first one is the aquifer uplift. So if the aquifer uplift exceeds the capacity or the weight from the floor, the mine floor sitting above it, it heaves the floor, it sends it into tension, and ultimately removes any confinement at the toe, thereby enabling the entire block to move. The other potential destabilizing force is the actual hydrostatic pressures within the coal joints. So there's a series of subvertical and subhorizontal joints. The subvertical joints basically become potential avenues for surface water ingress, which creates a phreatic gradient within the coal itself, which ultimately acts to potentially push the block out. The interseams, which are shown in gray, the interseams are sandwiched between layers of coal, and the interseams are generally moderately to highly plastic clays, and the effective strength mobilized by the interseams are governed by a number of things. Obviously, its mechanical characteristics, but also the weight of the coal. So essentially the normal force acting on the interseams themselves. So within a single interseam, based on the geometry that the blocks have been formed at, or the mine has been formed at, you'll get sort of disparate sort of potential shear strengths being mobilized as well. So there's a fair bit going on in this sort of context. The critical elements that need to be borne in mind are the aquifer uplift, the hydrostatic forces, as well as the shear strength of the interseams. Now, there is one small element I do want to mention around the coal. Now, unlike black coal, which has a specific gravity of, maybe between 1.4, 1.5, brown coal is quite a light material. It's got a specific gravity of around 1.1. So it's very similar to water. And so that does in itself pose a number of challenges, because we rely on the weight of the coal block sitting atop of the interseam to actually mobilize any shear strength. So we've got such a light block here, and we've got a number of forces acting to destabilize it. We do have to make sure we get that balance right. Otherwise our destabilizing forces will exceed the capacity of the system, i.e. will overcome the shear strength of the interseams itself and push the blocks out. So getting that balance is quite important, and that does have a bearing on the stability as well. So that's the coal blocks, that's the coal seams. Sitting atop of the coal seams, you do have a overburden layer, which is referred to as the Haunted Hills Formation. That's quite a dispersive material. It's sort of Emerson class 1, 2 type material, highly dispersive, and that does pose a secondary considerations in terms of stability. Things like your circular failures and things like that do come into play, and I will also touch on what happens to the coal seams when they're subjected to heat sources, a lot of which sort of naturally occur as a result of geochemical reactions. The coal itself, which is already quite a light material, effectively turns to ash. So those are some of the things that come into play. I did touch on the primary instability mechanism being the coal block sliding mechanism. So the importance of maintaining cold water gradients, so maintaining your hydrostatic forces as well as your aquifer uplift. Those two elements are very important within the scheme of things. But you do have a series of secondary instability mechanisms that come into play. What's referred to as kinematically controlled mechanisms, which are usually restricted to the coal layer, the coal seams, and they occur as a result of the geological features within it, so the joints, the bedding planes, and so on. So they can result in toppling failures where you've got subvertical joints. It can also get tetrahedral wedge failures where you've got intersecting joint sets, essentially providing daylighting in a slope face, providing an opportunity for large lumps or blocks of coal to fall out, but they occur purely within the coal and not within the itself. Now, how do we control within the primary mechanism, the coal block sliding mechanism? The way we really control are two key destabilizing forces, which are the hydrostatic forces within our subvertical joints. That's usually via a series of horizontal drains to intersect the coal joints, the vertical coal joints, to drain the water level within them and to ultimately drop the gradient. So that's how we manage the coal water gradient. And the hydrostatic forces are the ones that really, on a day-to-day basis, on a week-to-week, month-to-month type approach, particularly with any seasonal rainfall events and so on, those are the ones that really cause us the most challenges, the most problems, because anything more than a 10 to 15 mil rain event would probably charge those coal joints to a point where it can start pushing blocks out. The aquifer pressures, the underlying aquifer pressures, they're usually controlled by a series of redundant depressurization bores. So that's a system that we can actually engineer with some level of redundancy in there. And in some ways, whilst it is a very critical mechanism, and if left untreated, it can naturally heave the floor and cause quite a large scale instability mechanism, it is at least something that is we have the ability to control with the benefit of redundancy. It's a little more reactive on the surface water side of things, particularly managing your coal water gradients, because you are reliant on the joints being charged up to a point where they intersect the horizontal drains to actually dissipate any water. So it is very much a reactive management system, but they both go hand in hand. I did touch on the kinematic mechanisms. Not too many people are particularly familiar with how a tetrahedral wedge failure might look like in a brown coal slope. They look very different to in terms of its physiography, it looks somewhat different to what a tetrahedral wedge failure might look like in a hard rock mine. So I've just included a photo here, but typically, given the limited persistence of these joints within a coal batter, they barely affect a complete slope, so what's referred to as the global slope. They typically are restricted to a bench scale, so 1 or 2 bench scales, because they barely have continuity beyond 10 or 20 meters. That's the joint length. Okay, so that's just a little bit of background on some of the geology, how the geology impacts the stability and the potential failure mechanics of a potential block slide, or indeed a secondary mechanism, the kinematic mechanisms, just generally speaking in the Latrobe Valley. So now I want to launch into our subject area, I guess the subject of our case study. So this is a plan view of the Loy Yang mine. To the north of the Loy Yang mine, you can see the township of Traralgon. So it is located quite close to Traralgon. And our subject area, what I've referred to here as the area of interest, is quite an interesting sort of little anomaly within the site itself. This is an area that since about 2007 has been subjected to spontaneous combustion. Now, I'm not a geochemist. However, there is a particular reason owing to the mineralogy within the coal within this particular area, and also the presence of particular and persistent joint sets which have the ability to aerate and oxidate the coal within that area. It does from time to time, every couple of years, it does catch fire. And that then poses a real issue to this particular domain, because this domain, and I've just taken included a picture here which just shows a more close-up view of the southern batteries of Loy Yang. It does host all the critical infrastructure that carries the coal from the face essentially to the raw coal bunker, which ultimately gets into the power station for the purposes of burning. Now, there is a unique element with brown coal as well. Now, unlike black coal does have a relatively good shelf life, as in you can build up stockpiles of it, so that you don't never find yourself in a shortage of the material. So you can build up quite substantial stockpiles next to your power station and sort of periodically burn it, even if you have issues within your mine that might affect supply. Brown coal is quite a unique beast because it only has a shelf life of about 48 hours. And that was something I never appreciated till I started working in the Latrobe Valley and with brown coal. So a lot of the times I hear from people, well, why don't you just build up more supplies or stockpiles of coal? So should you have an issue on your mine, stability issue and so on that might affect production, you can always chew through your stockpiles. But in this case, the material is basically unusable after 48 hours. So the concept of building up stockpiles while prudent is actually not applicable in this particular area. So our subject area here has been quite problematic since about 2007, more specifically since 2010, and it has been subjected to periods of where it does flare up, and it has to be treated. Now, here's a photo of sort of what it looked like and what was happening when this event occurred in 2020. And what I'm touching on here is sort of what we were confronted with back in 2020, 2 years ago, when this particular area of the mine, which was carrying and hosting a lot of the critical infrastructure, which was the subject of a lot of scrutiny from the mining regulator, because the mining regulator is under a lot of pressure by the energy minister over here to make sure that supply from this particular mine is not affected by any unforeseen stability issues or indeed any issues around the mine, because ultimately this particular mine supplies over 60% of the state's power supply. So I guess when this particular event did occur, noting that it did occur on a critical domain within the mine, there was a lot of scrutiny around how this was going to be managed, remediated and maintained, all while supply wasn't being affected. So there was a lot of scrutiny around this particular domain of the mine. Now, the company, which is AGL, they were very they'd given us terms of reference, I guess, as their consultants, to make sure, obviously, we came up with a design to achieve a safe and stable rehabilitation outcome. Obviously, they wanted the key infrastructure, which is the conveyors, protected. It was quite unfeasible to relocate it. at that particular point in time, for that particular domain. It was also very important that the final remediation profile adhered to what's referred to as industry best practice criteria, which I'll touch on shortly, and make sure that whatever remediation objectives are put forward now and whatever is implemented can ultimately be sustainable in the long term, and ultimately won't have any repercussions down the track. So from that perspective, I guess we really had to launch into an investigation to work out what. Now, obviously, we saw the surface expression of what the spontaneous combustion looked like. Now, on the surface, you might see a little bit of coal, and some of the coal on the surface might have turned to ash. But deeper within the slope, there was essentially a fire, an inferno, sort of burning with temperatures exceeding 400 degrees Celsius. So we had to actually come up with a way of mapping out what was going on down below. So working out what areas were actually affected. It was important that we understood what now the material that was heat affected, what that heating process actually did to the mechanical conditions of the material. Now, obviously, if it's partially heat affected, some of the interseam materials will get baked, and that actually gets quite indurated and quite hard, whereas the coal turns to ash. And then you've got everything in between that as well. So it was quite important that we delineated those zones. So we used a series of geophysical techniques, because drilling holes into this material was not feasible, because the very process of drilling holes into the coal further aerates it and provides an ingress point for oxygen, which further exacerbates the combustion. So it was very important that we did not exacerbate or did not further aerate or provide further fuel to the fire. So we came up with a non-intrusive way of investigating this particular site. Now, I won't go into the details of the geophysical investigation. However, what we did use a series, a combination of what's referred to as seismic refraction and electrical resistivity. Both of these tools enabled us to, from the surface, non-intrusively map what was going on underground, identify the areas that were heat affected, and through the seismic refraction process, actually back calculate moduli for the heat affected material. The moduli can be attributed to strength parameters like your conventional cohesion and friction. The electrical resistivity was quite a useful tool, because, as I mentioned before, the coal within the slopes itself were actually being aerated through a series of continuous and persistent joints, which were actually connected and daylighting to the surface. So interestingly, if we could map those particular joints, and noting that those joints would be quite narrow features, albeit persistent in length. Those features were the ones that were essentially providing the ingress points for oxygen. So identifying those and smothering them, effectively starving those joints of oxygen, would at least control any potential sort of further exacerbation of the heating or the combustion. So that's how we sort of investigated it. That's how we delineated the sort of area of interest, what was going on down below, and how we worked out sort of the mechanical characteristics of the materials which we weren't able to conventionally sample for obvious reasons. Now doing the stability assessment was quite an interesting and also challenging aspect, because we were dealing with a dynamic environment. Now, in the context of heat-affected coal weather, one of the things that we had to do was obviously douse it periodically with water. Dousing these coal matters with water, whilst that does obviously alleviate to some extent the spontaneous combustion element, if you remember back a few minutes what I mentioned around the surface water ingress into the subvertical joints, providing the elevation in hydrostatic pressures, which is one of the primary destabilizing forces. It sort of enables us to appreciate that whilst the water's beneficial in mitigating the combustion, it actually provides another geotechnical risk because we're actually saturating and increasing the phreatic gradients within the coal itself. Additionally, the coal that is burning, the coal that started off with a specific gravity of 1.1, as it burns, its specific gravity is dropping. So the confinement that it invokes on the underlying interseam is progressively reducing. So you're in a very precarious situation here, whereby the confinement that invokes shear strength along your interseams, that's reducing because your coal is turning to ash. Further, by saturating the material, you're adding another destabilizing force. You've got so many dynamic elements to contend with. So taking a deterministic approach proved to be not the best way forward on this. So we went with a risk-based approach. So essentially, rather than going with singular values for material strengths, groundwater gradients, and so on, we looked at a range of upper bound and lower bound scenarios, and essentially modeled this this whole system stochastically. Now, we employed a particular system referred to as the Mine Geotechnical Risk Index, which was a system that I actually came up with a couple of years ago when we looked at the closure of the Hazelwood mine, which was specifically tailored to looking at the variables that go into the calculation process for your stability calculations for the block sliding mechanism within the brown coal setting. So there's a paper that I published on that a few years ago, which came out at the Australian Centre for Geomechanics 2019 risk conference, which sort of deals with that approach. Now, I am conscious of the fact that there's not too many geotechnical engineers necessarily sitting in the audience, so I won't labor those technical elements, but functionally for the mechanical and the process engineers within the audience, what we essentially did there was look at the various parameters controlling the destabilizing and stabilizing forces within our system, looking at credible upper and lower bounds and throwing all of those into a stochastic model, and ultimately doing a Monte Carlo simulation around various outcomes, so various upper bound groundwater gradients, lower bound strengths, bringing all of those together to look at how our factors of safety would vary across different conditions, and to essentially work out a reliable range of factors of safety. So that's the process that we went with. Now, within the context of mining geomechanics, particularly within Australia, North America, most parts of Europe and Asia, the generally espoused design acceptance criteria, it's colloquially referred to as the Reed and Stacey criteria, but it's the CSIRO pit slope guidelines, which sort of gives us a series of minimum criteria. So it's like a design standard. So if you're designing a slope in a given serviceability context, this is the factor of safety and ultimately the probability of failure that you would have to adhere to. The challenge for us was to essentially remediate this better, this particular slope, to get it up to a long-term factor of safety of 1.6. Subsequent to remediation, which was the minimum requirements for any within the Latrobe Valley for any critical matter that's carrying critical infrastructure. So that was a non-negotiable that was set in stone essentially by the mining regulator as well, and that was very much a requirement. However, during the process of remediation, there was acceptance that we would naturally be falling below that particular factor of safety. And as long as there were a series of, there was understanding around how far below that acceptance criteria it falls, and that there were some mechanisms and processes in place to manage the outcomes as a result of that, we were able to sort of get it through the regulator. Now, I won't go into all the ins and outs of the MGRI approach, but really what that is really a consequence assessment based on the likelihood of a particular event occurring. So if anyone is interested, I'm quite happy to send you guys a copy, or it's available online. It's a free download from the Australian Centre for Geomechanics, the 2019 paper, which sort of builds on work that was done by one of my former lecturers, Professor Peter Lilly, which looks at the likelihood of a particular event occurring, and that being sort of compounded by another extreme event. So in the context of this particular slope scenario, what was the likelihood that we would encounter a joint that was significantly degraded, that also sat atop of very low strength interseam material and had a temporally elevated phreatic gradient. So it looks at the likelihood of each of those occurring and what the return event on each of those events occurring would be, and then it rates a sort of a consequence factor at the end of it. So that's some of the approaches that we undertook in this to work out what our upper bound and lower bound strengths were for the particular system that we were dealing with across the multiple interseams within this particular area. So I've got just a schematic here which shows the area of material we'd identified from our geophysical investigation that needed to be removed, that was heat affected, which was basically ash and slop that was not providing any benefit in being there. But by removing that material, we are reducing the weight of the coal blocks, thereby reducing the shear strength mobilized along the basal interseam. So naturally, once we remove that material, we will have a temporary drop in the factor of safety. But noting that for the long-term conditions, we needed to bring that factor of safety back up to 1.6. So it was important that we reformed the slope with suitable material in a staged manner so as to ensure that we got back to where we needed to be in terms of factor of safety. So one of the things we were able to do as a result of that process is come up with a bit of a sequencing approach to how this remediation will be done. So we went with a top-down approach for the remediation. Naturally, it would have been much easier from a mine production perspective or an earthworks perspective to start from the bottom and work our way up, as opposed to the other way around. However, starting from the bottom and working our way up would have probably released too much confinement at the toe prior to actually building reforming the slope to invoke a sufficient degree of shear strength up dip of the critical area. So through the probabilistic process, we were able to test the respective outcomes across each of the excavation stages to work out what our critical groundwater levels were. So at each stage, we were able to work out, right, once we've excavated the hot material from, say, stage 1, we could test our models to work out how much further we could push the phreatic gradients within the slope itself, so we could preemptively cool the second stage and the third stage and so on. So that gave us a pretty good level of fine-grained resolution, I guess, across each of the stages to really come up with the critical elements, the critical aspects driving stability on each stages of the excavation. So that sort of really was a very useful tool, noting that we had quite a few variables. We had the material strengths within the coal, within the interseam, as well as the hydrostatic conditions as well, all varying within the system. All right, so that enabled us to sort of undertake or rather defend the remediation plan that was put forward through this process, and really gave us a really good understanding of which stage was quite critical, which stage was required the careful consideration of tarps, careful considerations of critical groundwater levels, monitoring, and so on. So this was sort of a challenge which we would not have been able to do in a deterministic sense using singular or conventional stability calculations. We really had to look at the range. The only way we were able to sort of defend and justify this to the mining regulator, particularly during the remediation phase, where we ended up with fairly marginal factors of safety, noting that we felt we had a pretty good understanding of what the drivers, whilst the factor of safeties were low, we felt we had a good idea on what the consequences of any potential movement were, and what the thresholds of the system within that within those confines were as well. So we wouldn't have been able to do sort of get this through and implement it without undertaking a risk-based probabilistic approach. And we ultimately were successfully able to remediate the slope. And here's just a bit of a representation on the right-hand side as to what that area looked like. So it was quite a precarious situation whilst we were working up to it. It was certainly something that I'd never dealt with in my career, and particularly at the Loy Yang mine, there were a number of people. There were some people that spent most of their careers there with 30, 35 plus years experience, who had, whilst they had encountered in localized and isolated settings spontaneous combustion, it wasn't to this extent, nor was it this close to a critical matter. So this was certainly something that was quite unique, given the scale and the location that it occurred at within Loy Yang, and the level of scrutiny from the regulator on this particular one was quite high, as well as AEMO. And for the Australians within the audience, that's the Australian Energy Market operators. So they're the ones who basically advise the federal government on the minimum reliability requirements for, within Victoria, it's, what the minimum production requirements are for power and things like that. So there was a lot of scrutiny, not only at the state level, but also at the federal level, on how this sort of project turned out. So look, I'd like to sum up by saying this particular paper was also published at last year's Australian Centre for Geomechanics Slope Stability Conference. Again, it's one that's available online, and in the paper, I have dealt into, for the geotechnical engineers within the audience, or indeed mining engineers, I have dealt into a little bit more of the mechanics of the calculations, if ever anyone's interested in looking at that. But I'm also happy to have a chat around that. But the paper ultimately demonstrated how important it was to, in situations where you're dealing with multiple variables in a dynamic setting, how the main way forward is looking at a risk-based probabilistic approach, because you're not dealing with a singular set of parameters. You're dealing with a range which vary in 4 dimensions. So not just your X, Y, and Z, but also time. Because as if a coal bed has been burning for an hour versus if it's been burning for 10 hours, the properties from hour 1 to hour 10 vary quite significantly, and that has a bearing on our overall stability of the system that we're looking at. Now, I've dealt purely with the design elements, which are arguably quite philosophical. There is another part to this presentation which I haven't touched on here, which was actually how the works were implemented, because it's all well and nice for us to do these calculations, on pen and paper or computer models, but it had to be implemented very carefully in the field to make sure that it was adhering to the design intent. So there's a whole piece around the quality assurance and the quality control. Now, thankfully, on this particular site, we did have a very good contractor, very knowledgeable and experienced team was put forward on this to make sure that everything was done, done to quite a high level, noting the scrutiny that we had on this. So look, that's like I said, that's the end of what I had to say. But if anyone's interested, the paper is available online through the repository with the Australian Centre for Geomechanics, and I had a lot of good help with my co-authors, Nirav Patel from GHD and also Anthony Simons, as well as AGL, because our client, AGL, was very supportive in us doing this work, and sort of gave us a lot of latitude to investigate this. And they also appreciated the nuances and the uniqueness of this particular situation that we were bestowed with. So look, that's the end of my presentation. If I haven't put anyone to sleep, I'm happy to take questions.
Mhm. Yeah. Thank you, Sanjeev. It's very interesting because we in Western Australia, we have less knowledge and exposure to coal. And so therefore it's a unique area for us as well. And there's a lot of things to learn. And before I open floor for questions, so I have a question, one thing before I start this. And you said that there's a limited time, well, lifetime for brown coal. You said 48 hours. Could you please explain further on this, please?
Now, I'll have to preface that by saying I'm not a geochemist. Now, what happens apparently after 48 hours is this brown coal is quite high in moisture, and at the best of times, it's got a high loss on ignition anyway. But what happens after 48 hours is the material does turn to it does essentially turn to ash just by exposure and oxidation to natural conditions. So in the old days, when in Victoria, the coal mines are now run privately by Energy Australia and AGL, but in the old days, they were run by Victoria's State Electricity Commission. And in the old days, they used to make the raw coal into briquettes. And the briquettes would be, but that's another process. It adds another 4 weeks to the system, but the briquettes could last up to 3 or 4 weeks from memory, so maybe up to about a month. But at this point in time, they've decided they've dismantled all the briquette plants. So as far as it was explained to me by one of our resource geologists, who's also quite familiar with the geochemistry of coal, essentially the material oxidizes when exposed, and after 48 hours, sort of the energy you get upon burning is very minimal.
Okay, interesting. Thank you. So we are waiting for AI. Are there any questions from the other parts of Australia or other people? Members who have joined online, please. The floor is open if you wish to ask any question, or if you can write the questions on the screen, please. So till questions come, Sanjeev, I have a question again on geotechnical area. Just now you have described on your design approach to manage the walls. In this, I didn't hear anything about ground support. Do you use any ground support for stabilization purposes?
Yeah, good point. Now the coal itself, it's got a very low specific gravity, and the morphology of this particular coal, it is ubiquitously riddled with a series of joints. So the material is actually very, very blocky. It is, whilst the interseams are quite ductile, this material is very, very sort of brittle. So any ground support. So if you think of cable bolts or rock bolts, in the case of cable bolts, your plates will probably end up punching through the surface itself.
Exactly.
So that rules out cable bolts. There is arguably a call for strategically employing self-drilling soil nails or friction bolts. Now, we have actually trialed that not on this particular site, but on another site, and they were they had quite capricious outcomes because the jointing was so sort of frequent, because it's very closely spaced jointing. A lot of the times we didn't quite get the proper embedment. You know, we found that the friction bolts and embedding them, you know, the toe would be embedded in a potentially loose block, and we weren't quite getting the full friction along the entire element. So we did look at that. However, you do raise a very good point, Dr. Seneca. The form of artificial slope support that we do look at is by actually forming buttresses. So one of the things I did touch on is what's ultimately governing the stability of the coal blocks is the strength it mobilizes as it shears along the interseam. So the heavier the block itself, the more strength it mobilizes, right? So what we do is we artificially increase the strength of the block by strategically placing surcharges. It's quite important that you place the, we call them surcharges, but essentially they are, lack of a better term, buttresses to effectively increase the weight of the block, noting that we're dealing with material that has a specific gravity of 1.1. So by artificially pushing its weight up by placing compacted material on it, we invoke more shear strength. So that's the form of slope support that we primarily tend to go with. Sort of your mechanical anchoring and things like that are quite challenging through here.
Yeah. Thank you. I wish to ask from our control center, do you see any questions coming from the audience? So far, Sanjeev, we haven't seen any question coming here. I think I mean, so we'll, and another, I mean, while we are waiting for any more questions from the audience, and do you consider, I mean, the area where you are working and where these coal mines are there any seismic triggers, or are there any seismicity noted on these areas where you need to have more additional precautions to manage the walls?
Yeah, no, that's probably another good point. Again, yeah, much like yourself, I had prior to moving to the Latrobe Valley, spent most of my career in WA and other places. Comparatively speaking, the Gippsland Basin is geologically quite young. It's only about 50 million years old, so it is seismically active. Seismicity is an issue. And there is also the secondary consideration of reservoir-induced seismicity as well within the areas that have, like for instance, the Hazelwood mine. Now that they're allowing it to refill again, there are other considerations around it. So seismicity is an issue, certainly on a regional scale. In fact, we had quite a large seismic event last year, which sort of I think had a magnitude of about 5.7. Now, most of the events that we get through here, now for those of you who are familiar with seismicity, you get two types of events referred to as P wave events and S wave events. So I think Dr. Seneca, as you know, that the P wave events are generally the ones that occur sort of at depth and can usually occur as a result of sort of rock bursts and things like that, certainly in underground mines, but the S-wave events usually occur when they're shearing on particular features. Generally speaking, although it's not necessarily a hard and fast rule, it's the S-wave events that tend to be more destructive. Not always, but generally speaking. Interestingly, most of the events we've seen here are P wave or dominated events, which do obviously cause an issue with vibrations and so on. We haven't had any significant, and it does cause blocks to fall out and rock falls and things like that off berm crests, but it hasn't caused any significant instability events, apart from actually giving the slopes a bit of a jolt so far, anyway.
Okay, good. Thank you. Waiting for questions. Okay, so I think as far as I see, there are questions coming later on by email, and so I think from the IESL host will let us have those questions, and I can forward them to you, Sanjay. Yeah, and so at the end, I mean, it's also a very, very interesting topic, and really, I hope everybody enjoyed this, and there's a good audience as well. And so it's a topic that is not very familiar to us, and we have learned a lot here. And coal is a new area for me as well. So thank you very much again for very informative and very technical presentation today. And behalf of the IESL chapter, WA and IESL, whole community, I would like to thank you very much for your time and the presentation here, please. Thank you very much, Sanjay, for your presentation.
Thank you very much, Dr. Seneca and team for hosting me.
Thank you. So I think we'll see you at the next webinar, which will be put on online very soon. Thank you.
Thank you.
See you all. See you.
Cheers.
Thank you. Bye.
Bye.